So we'll start with questions from homeworks, if anybody has anything. So at this point, we've assigned up through, what, 1:30? Happy to do some homework questions if anybody has anything. I don't know if you're looking for stuff right now or if we're just like thinking, or Blake, we'll go with you.
Okay. Oh wow, I have a lot, but sorry. Number 116.
116. All right. Okay. So first thing you wanted to do would be what? Yeah. So that's going to give us negative log x plus 2 equals 2. Then what? How about divide by negative 1? To get the log part all by itself. Does that feel okay? And then to cancel a logarithm, what do we have to use? An exponent base. And the exponent base I want to use in this case is 10 because it matches the base on the logarithm. That's right. So 10 to the negative 2 is 1 over 100, or 0.01. And then we just subtract 2 from both sides. And if you go back and check that, if I plug that in for x, I get a positive number inside the logarithm, so that should be good. Maddie.
So when you have the 10 log to the x like minus 2, what do you do with that number? Do you just plug that in?
10 to the negative 2.
Oh, okay. So
I did it in my head, but you could type that in your calculator to get the 0.01. That'd be fine also.
And then you do 10 to both sides, right? Because,
I did exponent base 10 to both sides to cancel the logarithm. Correct. Blake?
129, please.
129. Okay. Just move back up here or something. You have the numbers in front of me. Okay. So we have natural log x minus 3 plus natural log x plus 4 equals 3 natural log 2. Okay. The observation I want to make here that makes this problem different than the previous one is that we have x's in more than one location. I have x's in 2 different logarithms here. So the first order of business is going to be to get one logarithm on each side, right? So what am I going to do on the left-hand side?
Just use the product rule.
Very good. Product property will take care of that. And you could FOIL those out at this point, but I'm just going to write it that way for now. And then on the right-hand side, I have that 3 outside the logarithm. What am I going to do with that?
Oh, you use power.
Power property. The power property allows me to move that into an exponent. So I don't want to divide there because it just then pushes it to the other side, and I have the same problem with a coefficient on the other side then. All right. At this point, since I have one log on each side only, I can use the one-to-one property and just kind of drop the logarithms. if you want to think about it as like
Oh, yeah.
exponent base e to
Yeah.
both sides, same thing happens. Either way, thinking about it is okay. But that's just using the one-to-one property that we mentioned at the very start yesterday.
Mhm.
And so what left here is the quadratic. So to solve a quadratic, it's got to be equal to 0. So if I subtract the 8 over, there's my quadratic equal to 0. To solve this, I could.
You could use the quadratic formula. You can just factor it.
I would prefer factoring in this case because I see exactly how it factors. Just multiplies to give me negative 20 and adds to give me positive 1 is 5 and 4. So if I go and I check now, if I plug negative 5 in for x, that's a negative. That one is extraneous. But if I take the x equals 4, positive, positive, yes, sir.
Do you have a calculator I can borrow?
Yeah, I think so. What happened to yours?
It died.
It died. Let's make sure this one has good battery amount on it. I don't know. It's best that here. Give me that one. I'll put it on the charger, and then I have some incentive for you to come back. Thanks, Domenico. Does that feel okay with you guys? Blakey, you like that? You guys don't like Blakey?
No, I love it. I think you should call him that every day.
The better question is, does Blakey like it? That doesn't sound...
Is that called? So that's called an extraneous solution.
Yeah, one that we get algebraically, but
Yeah,
doesn't
right,
actually
yeah.
satisfy this equation. Yes.
And the way you check that is by plugging it in for x, right?
Yeah, you're just looking to see if you get a negative inside one of these logs. Or I should say a non-positive, because 0 is bad also. Alex.
Can you do number 81?
Uh-huh. Let's see, that's a different page. All right. So 81, we have log of the 4th root of x over y. Okay, so this one we have to be a little bit careful about the order in which we're doing things. Alex, what was the first thing you'd want to do when we're expanding this? Yeah, so you wouldn't want to start with the quotient. You'd want to start with the power property here because that power is surrounding the quotient. So I remember that a 4th root is the same as a 1/4 power. So I can do that. So far, so good. Then what do you want to do? Well, are there any product properties that you see? Quotient, yeah. So what would we write then? Right, that's quotient property. Now I've written this wrong. There is a mistake here. I wrote it wrong on purpose. It's not plus. Yeah. Is that 1/4 is multiplying the quotient piece? So anything that comes out of the quotient piece needs to be multiplied by the 1/4 also. So there should be a 1/4 on the log y also. And that's our final answer. Is that okay?
Yes.
And again, if you wanted to go straight from like this step to this step, that's okay, right? Like you don't have to show the intermediate one. I just wrote it so that I could point out like the common mistake, you know. And it's notes, so like I'll over-explain everything kind of, you know. It's my job. Who's next? Anise? 82. Okay. So, Anise, what's the first thing we'd want to use here? I would not do that first. Yeah, this one you should do the quotient first, since the 1/3 roots are not around the entire inside part there. It's only around single variables. And then we can do the power property after that. It's worth mentioning here that if you wanted to, you could use your properties of exponents on the inside to rewrite that problem in that fashion and do it the same way we did the first one. Or on the first one, you could take your properties of exponents and rewrite it like that and do it the same way we did the second one. Either approach is fine. If you want to manipulate your exponents a little bit inside the log to make the problem easier for you, that's okay. If you're not sure how to do something, you can always fiddle with that. Is that cool, Anise? Okay. Alex, 92? Sure. Okay, so here we're condensing. What's the first thing you want to do here, Alex? No. Powers, yeah. So do we see power properties? Yeah. And this here we have to be a little bit careful because I know the power property has to apply to everything inside the logarithm. So I'm going to use like that extra set of parentheses there when I move them inside. And then I can look for my product property, which we see, right? Okay, and now I'm going to write this as simplified also. So I'm going to have an x to the 9th, y to the 3rd, y squared, and then a z to the 4th. Because an exponent of an exponent, we multiply the exponents. And then you notice that, hey, I can take those y's and put them together. And that's probably as good as you do there. Does that feel okay? Sure. Blake.
Number 128, please.
128. Sure. Let's see, we have log x minus 1/2 log x plus 4 equals 1. All right. First thing you want to do here, Blake. What do you think?
First thing, I did the power property.
Good.
Then the quotient.
Yeah. So that's eventually going to take me down to that, right? Everybody cool with how I did that? If you're not sure, holler at me, but I combined 2 steps there, right? All right, we got to get rid of that log. How are we going to do it? Exponent base 10. Yep. So I'm just going to kind of cheat my work there a little bit because I didn't leave myself very much space here. 10 to the first is just 10. All right. What do you want to do here?
You can multiply like both sides by x or x minus 4.
Okay, that sounds good.
X plus 4 or x minus 4?
Oh, is the problem? I wrote down x plus 4.
Oh.
In the problem.
No, I just I thought that I wanted to get rid of what you call it? I wanted to get rid of all of the.
Right. So let's do this. Square both sides to get rid of the root. Is that what you're saying?
Wait, I did something different. So I just multiplied both sides. Wait, no, but that wouldn't work. Yeah, I think that's right then.
This is what I'm doing is correct. Yeah, for sure.
Okay, I'm doing something different.
Okay. So the place you have to be careful there is when you square both sides, you have to make sure you square the 10 in addition to the square root x plus 4. That's a common oopsie. So we're left with a quadratic equation. So I'll move it all onto one side. And let's see, multiplies to give us 400, adds to give us 100. Oops. Let's see. We got 8 times 50. We have 16 times 25. I don't think it factors. Do you? No. So we're just going to do the quadratic formula. I don't have enough space to write it, so I'm just going to say what I did. Is that okay? All right. And I'll just do it on my calculator. So I have negative of negative 100 plus or minus. I'm just going to start with the plus. Square root. Well, let's do it this smart way so I can reduce the radicals and stuff easily. So I have the inside, that's the b squared minus 4ac. So that's that. Let's just make sure it's not a perfect square. Okay, it wasn't. So I can divide that by 4, divide that by 4. And divide that by 25. Okay, so I have 20 square root 29. Bless you. Or 50 plus or minus 10 square root 29. And then I just have to make sure that minus 10 times the square root of 29 isn't negative. It is. And since that's negative, I know when I go back and I check, that's going to fail. Right? So I'm only going to have the 50 plus 10 root 29. I think. Presuming I didn't make any dumb arithmetic errors, I tried to do that without having to write anything down. You know what I mean, Blake?
I do, yeah.
Others. Blake.
Sorry. 136.
136. We haven't gotten there yet.
Oh, I thought that
No.
it was up to 138.
Oh, have we done that? Okay.
Wait, no. Oh, bad.
No, I'm still
130. Jeez.
right. We haven't done the other half of section 15.4 yet, right?
He was looking at the regular.
Oh, okay. I just want to make sure too. Like, yeah,
I was
yeah. Okay, we haven't done that yet. That's what we're doing today. So we'll do 131 to 138 lecture today. The stuff for that. So I'm just going to table that till next time. Is that okay, Blake?
That's fabulous.
Okay.
I want to do it in one word, so I have to.
Yeah. I mean, you're going to have to do it eventually.
This week.
Maddie.
Can you do 100, please?
Sure. Okay. Here we go, Maddie. 132 times 1/4 to the x over 3 equals 2. What you want to do first?
I'll divide 32 by something I found on the other side as well.
Okay. All right. Now what?
And then, don't you want to do something with the fraction that you got? With the 1 over 16?
You can do it that way, sure. How do you write 1 over 16 as 1/4? Or as a base 1/4?
1 over 4.
How about squared,
Oh, squared, yes.
right? Because 4 squared is 16. Sure, we can do it that way. And if you do that, you can just drop the exponent bases and set the exponents equal to each other.
Okay.
So we get 6. Neato!
And then you just plug it. Then you plug it back into the original equation.
You don't even have to check the exponential equations. These should work. Yeah. These should always work. The logarithmic ones you should check. The exponential ones you don't need to. And the reason there is that an exponential equation, the domain for an exponential function is all real numbers. And a linear equation, the domain, or a polynomial equation, the domain is also all real numbers. So anything you solve for in the polynomial should work in the exponential.
Okay.
That's not the case for a log, right? The domain for a log is 0 to infinity. Polynomial is negative infinity, positive infinity. So there's possible answers to the polynomial equivalent that are not going to be solutions on the logarithmic.
Okay. Yeah.
But that was more explanation than you were probably even looking for. It's okay. Alrighty. Anybody else? Cool beans, kiddos. Today, we're going to finish up section 15.4. So in section 15.4, we've been talking about solving exponential and logarithmic functions. Today, we're going to do some real-world examples of that kind of thing. So we're just going to look at some real-life systems that can be described using either exponential or logarithmic functions. So the first system that can be described using either an exponential or logarithmic equation is the sound intensity. So the sound intensity, anybody know what sound intensity is measured in?
Hertz.
Nope. Decibels. Yeah. So beta is just going to be our number of decibels. And for the record, decibel is the abbreviation is dB, where the D is lowercase but the B is capital.
Why isn't it D capital?
Because the prefix for deci is a lowercase d. You know what I mean? Yeah. I is our sound intensity. And the measurement for sound intensity is like watts per meter squared. And I naught is a constant. All right. Given the sound intensity of busy city traffic is approximately 10 to the -5 watts per meter squared, what is the measure of busy city traffic in decibels? Hopefully, nobody's confused at why we'd be choosing to use the sound intensity model here, since it's talking about sound intensity and decibels in the thing. Okay. What are we solving for? In this equation, what is the question asking us to solve for?
No, measure of busy city traffic in decibels.
So that would be which variable? The beta, yeah. Good job. Okay. And then where does the 10 to the -5 go?
Intensity of the number.
The sound intensity, that's the I. And then remember that I naught is a constant. So when I type that into my calculator, I don't even need my calculator for this. Just 70. Right, 10 to the -5th divided by 10 to the -12th is 10 to the 7th. Log of 10 to the 7th is 7. 10 times 7 is 70. Or you could type in your calculator if you'd like. Nothing wrong with doing that. Not all of us are mental math wizards. It's the constant, right? That's always the lovely answer, right? It's like, oh yeah, it's just always that. It's like, you know. All right. Oops, that's not how you spell it. The next model we'll look at is the Richter Scale. What is that used for?
Earthquakes.
Yeah, measuring earthquakes. You're thinking of the Mohs scale is for hardness. How's that for Mr. Kulik, pulling that from nowhere? Okay, the Richter scale equation. R is your Richter scale magnitude. And I'm just going to say EQ for earthquake. Is everybody okay with that? That's a lot of letters. Alpha is the amplitude of the earthquake. And we measure those amplitudes in micrometers. I think that's the mu, right? Is that the prefix for that? Science people, I think I'm right there.
What letters are those for amplitude?
That's the mu and an M, micrometers. Mu is the Greek letter that looks like a double. It's supposed to be like an M, but it looks more like a U to me. So I always kind of just think about it, a U with two tails on it when I write it. But it's supposed to be the lowercase letter m.
Looks like a very weird M.
Yeah, good. Then that's what it's supposed to be. Yeah, weird M. Great. I'm better at drawing these than I thought. So when you think about an earthquake, the earthquake part is like the earth moves up and down, right? Anything moving up and down can be described like with a wave. So the amplitude is like, if this is base level earthquake, it's like the maximum distance that the earth is kind of shifted up or down. Everybody feel cool with what we're kind of describing here? It's all math, man. That's the purpose of it. It should be able to describe the real world. T is the period for that associated wave. So again, the period, if this is base level Earth, goes up, goes down, and then goes back to base level. One period is the amount of time it took to go up, down, then back to base level. Is that all remembering this first semester trig idea or vocabulary? I just want to make sure we're cool with that. Now, where is an earthquake the strongest? The epicenter, great. And as you move away from the epicenter, what's going to happen? It's not going to be as strong, right? The earthquake won't be as strong. So we need like a correction factor because our tool that we measure the displacement happening isn't always located exactly at the epicenter, right? So this B here is going to be a correction factor for like the weakening of an earthquake as you move away from the epicenter. It's basically just to make sure that like, hey, if the earthquake is in San Francisco, but my like Richter scale contraption, I don't even know what it's called, the tool that measure, but if that's in like Sacramento, like we have to have some kind of correction because you're not going to get the full intensity of the earthquake. So this is like a correction factor. All right, let's see. The infamous San Francisco earthquake, I think it's referred to that as it's probably the strongest earthquake in the continental United States. Notice I say continental, not counting Alaska or Hawaii, that are more also situated on that ring of fire plate. Has a magnitude of 7.5. How many more times severe was the most severe earthquake ever recorded? The 1960 Chilean earthquake that had a Richter scale magnitude of 9.5. So hopefully from reading this, everybody is pretty convinced we should be using our Richter scale calculation. Everybody feel good there? And we're given two Richter scale measurements. So what do you suppose we're going to have to be doing? We're going to have to be solving a system of equations, right? We're going to have an equation for the Chilean one and then an equation for the San Francisco one. Now, I guess before we get going too far, let's pause here and talk for a moment, because we're going to do a little bit of hand waving here. So these Richter scale measurements that we've been given have already had the correction factor applied to whatever measurement they took on the earthquake, right? So we can assume that the B's are both essentially 0 that are associated with this because we have the already corrected Richter scale measurement. Does that make sense to you guys? Since we're looking at the thing that's already been corrected to, like, this is how intense it would be at the epicenter, we can just assume the B is 0, or you could assume the B's are equal. Either way of thinking about it is okay. Cool with that? The other piece here, when it asks for how many more times severe, the severity of the earthquake is going to be described by, like, the displacement from whatever normal Earth is, right? So we're looking for a ratio of the alphas. Is that cool? One more assumption we're going to make is that the periods are going to be the same. Okay? Because we're not given any information about the periods, we're just going to assume the periods are the same. Okay. Okay, so there's my system. Again, we're assuming that T1 and T2 are equal and B1 and B2 are equal, so I just called them both T and both B.
Could you get rid of them?
Well, you can't get rid of the T's.
Because it's inside of the log.
Yeah, we need to have those there. But we'll show you what's going to happen here. So let's solve this system. I'm going to solve it using elimination. So I'm going to subtract the Chilean equation, or subtract the San Francisco equation from the Chilean equation. I'm going to choose to do it in that order because I want this to equal a positive value, right? You're going to have big problems potential. Well, not. I guess you won't have big problems, but it won't be. Yeah. It's just going to look nicer. But is it cool with what I did? I subtracted the right or left-hand sides and subtracted the right-hand sides. Except I wrote that in the wrong spot. This is alpha 2. That's alpha 1. My apologies. Okay, so I can distribute the negative sign here to do that. Everybody's cool? What do you notice I can do now? Yeah, the B's are just going to cancel out. What else can I do there? Quotient property. Yeah, exactly right. And since they're both fractions, instead of writing it as a fraction, I'm going to write it like with a division symbol. Is that okay with you guys? How do we divide two fractions? Yeah, so back in elementary school, they told me dividing fractions is easy as pie. Flip the right and multiply. And I still remember it, so it must work. Everybody's so far so good. Next, what do I do? Yeah, exponent base 10 to both sides. So I'm just going to kind of do some cheaty and write this. Is everybody cool with me doing that? If you're not, holler at me, but actually we'll do this. So we have that the Chilean earthquake then is 100 times more intense than that San Francisco earthquake. Ooh, doggy.
Sorry, how did you get the 100 times?
10 squared. It's 100. Cool. Okay. What do you guys think? Still doing okay? Not too big of a deal. Next up, our next model is the pH scale. What does pH measure? Yeah, it's the acidity of a substance. Okay, so what values of pH are for acids? Chemists? Come on, guys.
1%, right?
Acidity is like 0 to 7.
There you go. And base is?
Base is
7 to 14.
7 to 14. And what's neutral?
7.
Thank you. Good job, guys. You remembered it. It took a minute, but that's okay.
We don't talk about chemistry class.
Oh, excuse me.
Chemistry was traumatizing.
And this symbol, what do we, when we put brackets around a chemical substance, what does that mean?
Oh, it means that they gain an electron.
Nope, it means concentration.
Wait, is it? I thought that's what it was. No, that's what the little plus sign is for.
The plus sign means it lost an electron.
Crap.
But the bracket means concentration. What do we measure concentration in most commonly in chemistry? Use molarity, which is moles per liter.
Yeah, I knew that.
Is it bad when your math teacher knows more chemistry than you do?
I mean, chemistry is bad.
Hey, in fairness, guys, I have an undergraduate degree in chemistry, so it's like kind of not fair.
Second nature for you.
Yeah, it's quite easy.
If you want to my chem,
I don't get this. You just eat the lemon, you're like, wow, this is really sour. I'm gonna measure the pH of this.
All right. So we have the following question here.
That's like an incredible, that's a dangerously acidic lemon. I thought that lemons were like a 6.
You're dangerously acidic.
It's really
That's like
sour.
stomach acid, isn't it?
Like, it's a really sour.
It's really sour.
I see. That's pretty valid.
Yeah, it's not just any old lemon. All right, we have a really sour lemon is found to have a pH of 2.2. And a bottle of bleach is found to have a pH of 10.2. What are the hydrogen ion concentrations of the two items?
This explains my grade in chemistry so much. Yeah. Oh, you're right, I need to.
So first time in chemistry is everybody first time since I left.
No, there was, I had a mole question on the ACT. I had a mole question.
I had a
Okay, so let's solve the lemon equation first. What do I need to do that? What should be the first thing I do?
Tell the lemon to be less acidic. That's gonna kill somebody. That's like 2.2. Doesn't it say like?
It's really sour.
Wouldn't that kill somebody?
It's all about, look, the rule of thumb is dosage is what matters.
This is like when we went
yeah.
This is like
There's a little bit of stomach acid.
Bob, we bought like 80 watermelons. Like, why is Bob buying 80 watermelons?
Take out the negative and then do like the base 10.
Very good. So the first thing I want to do is divide by -1.
No, I don't care. You need to stop buying these.
And then we can do exponent base 10 to both sides. So 10 to the -2.2 is 0.00631. Or I can call that 6.31 times 10 to the -3rd. Everybody's cool? Okay, I do the same thing here. And I get 10 to the -10.2. I skipped all the algebra steps. Everybody's cool with that because it's the exact same algebra. Oh, boy. So there I get 6.31 times 10 to the -11. Everybody happy with part A? Okay. Part B says how many times greater is the hydrogen ion concentration of the bleach than that of the lemon? I think that this question is probably asking, those should be worded the other way. When we talk about times greater, we're talking about what operation? That would be division. So that lemon is 100 million times greater hydrogen ion concentration than the bleach. Well, bleach is pretty basic too. You know, let's be clear here.
Yeah, because you know, bleach would always be safer than a lemon.
I divided
That was one heck of a
this
lot.
number by this number.
Okay.
I just did it in my head instead of on the calculator. You know. And you could just, you know, which rounds up to 100 million or 100 million. Same thing, right? No problem. Good question.
According to the old Google, the average one is around 2 on pH 2. That's like really acidic. I'm surprised.
Again, dosage matters.
That's true.
Dosage matters.
Wait, what is that?
Not enough to kill you.
Just take the mystery pill that Mr. Smith gives you in his class and you won't taste it anymore.
If I had to choose one.
Yeah, we were really about 7 and he told us to eat something, so we all ate it, and like it made like pure lemon juice, just like it was really good. I had like a whole glass of lemon juice.
Wait, this is.
Oh yeah.
All right. Last model is called Newton's Law of Cooling. So Newton's Law of Cooling is as follows. I sure hope so. Sure. So when does this situation apply? If you take a hot item and you place it in a cool room, it allows you to predict the temperature, you know, T minutes after placing it there, right? That's the idea. So like if you're a chef and you baked a pie and you want to know like how long before I can serve this thing, or if you've microwaved some pizza rolls and are sick of burning your mouth because they're biting into liquid lava, this would be helpful to you.
You eat it and you tuck it through. For pizza rolls, you eat it and you tuck it through.
Bite the corner.
Do the weird like breathing. Nah.
Or if you're like a medieval blacksmith and you're like making swords or something. You're back. How did it
Oh
go?
wow, better than I expected.
Good. I'll take that. Take care, Domenico. All right. So what do these symbols mean now? So the T of T is the temperature of the substance in question. T minutes after removing from heat. Tm is the temperature of the surroundings. The M is for medium, but I find that word to be kind of confusing. So if you're letting your pizza rolls cool, the temperature, the Tm would be the temperature of the room. You know, if you're a medieval blacksmith and you're forging a sword and then you dip it in the cold water, the Tm would be the temperature of the cold water. I think that process is called annealing, where you're trying to get that sword really hard and strong.
You learned about that chemistry, you got to do that.
See, there you go. It's almost like all these subjects are somehow related.
Math is in everything.
The T naught is the temperature of the substance when it's removed from the heat. The K is a constant. Now that constant is specific to a substance. So like the constant for a pizza roll would be different than the constant for a steel sword. Which makes sense, right? Like clearly like you make some soup on the stove and like you make a grilled cheese sandwich and those two things cool at very different rates. grilled cheese sandwich is usually eatable quicker than the soup would be if you take boiling soup off the stove. You know what I mean? And T is just your time since removal from heat. All right, let's see. Where are my chefs in the room?
No one trusts me to.
I like to cook.
Because we're boiling eggs here, folks.
Oh, it's so boring. Like, they're just watching.
All right, a hard-boiled egg is heated to 96 degrees Celsius and placed in a pot of cold water to 16-degree water to cool. After 4 minutes, the temperature of the egg is 45 degrees. How long will it take in total to cool the egg to a temperature of 20 degrees? Anybody have any doubts about the model we should be using in this case? Hopefully it's pretty obvious we're using Newton's law of cooling here. If we read this question, do we have all of the variables in question given to us? No, what are we missing? The constant. So what we're going to have to be doing is finding a way to solve that for that constant first. So when I read this question, like these first two sentences are going to be devoted to finding the k. Where we're given a specific situation, right? Like here, this is what happened and this was the result. We'll use that to find the k. All right, so the 96, where does that go? Where does the 96 go? What is the 96? It is not. That's the temperature of the substance when it's removed from the heat, right? That's the T naught. Okay. What's the 16 degrees?
TM.
TM, that's the temperature of the medium or of its surroundings. We have 4 minutes. Hopefully nobody has any questions that has to be the T. So the 45 then has to be our T of T, which makes sense because that's the temperature 4 minutes after removal from heat, right? Okay. Solving for k here, where's the k located? In the exponent. So eventually to get that k, we're going to have to use a logarithm, but not yet. What do we need to do first? Subtract the 16. And then 96 minus 16 is 70.
Whoa, 80?
That's what I meant. Thank you. Mental math is hard sometimes, guys. I can do these logs in my head, but then I screw up 96 minus 16, so go figure. All right, now what? Divide by 80. Yeah. Now it's time for which one? The natural log, ln. Everybody's cool with y? Ln is log base e, and that's our exponent base. Is it okay that I kind of skipped writing all this, all the intermediate steps? These kind of end up being a lot of the same things. So I just, at some point, you're just like, yeah, like that. It happens. Okay. And next, what I would do is divide by -4. I'm going to write it like this, though, so that when I go back and look at it later, I'm not confused at whether that dividing 4 is happening inside the logarithm or outside the logarithm. So I'm just going to write it as like times the reciprocal. And then it's calculator time, my dudes. Everybody okay with that, my G's? So I get about 0.254. So that's like the yellow part. Let's actually put it there. Okay. Everybody cool? Yeah? The next part of the question, the actual part of the question, asks find how long. So what are we going to be solving for? Time. Good. It will take in total for the egg to cool to a temperature of 20 degrees. What's up, brother?
So I'm taking 5.
Yeah.
And you said we could skip 2.
Yeah.
So there's some problems with multiple, like A and B and C and D. Does that mean just one of those or the whole problem?
A whole problem.
Okay.
Yeah. No problem. Yeah. If it's like number 7 and has 3 parts, you skip all 3 parts.
Okay.
That's one question. No problem. All right. Okay. So that's T that we're solving for, and the 20 degrees then would be our? That's T of T, right? Because the Tm isn't changing. The T naught isn't changing. Because it's still the same egg and just cooling further, right? Everybody's right on this. Same steps now, right? Ugh, throat tickles. You ever get those? Get a drink. All right, calculator time. -1 over. I'm going to steal all the decimal points from my from the previous one there, so I don't have to round my K. You know what I mean, guys? Give me a little bit more accurate answer. I get about 11.8 minutes. So this is like answering the green part of our question. What do you guys think? Again, very much just the solving problems. They're just now in story problem form. We needed these models to be able to like construct the actual equation. But that's the gist of it. How'd I go?
The second to last problem was impossible.
Okay, but other than that,
Other than that, it was perfect.
good. Alex.
Yes.
Yeah, I was the other Alex. Sorry, that was confusing.
That's a pretty Matrix moment.
I know, right? It's like there's a cat just paused and did the same thing it did a second ago.
This is
Is the whole world a simulation? Are you even real? You're just some lines of code going through my head, aren't you?
Yeah, like when you find out that if something's red, it's actually every color but red.
It's like everything only can reflect one shade of color, and so like that wall that you're looking at, or that I'm looking at, it reflects or it absorbs every single color except for one piece. Pretty cool.
Yeah. How much of the world is that we think is real is just a product of our like sensory system?
That's
My clue is not your clue, and that's.
All right. This feels like what do we got? Like 15 minutes left or something? Not even. Yeah. Let's just stop here. It's okay.
Yeah. Can you still have it? Really? That's deep. Oh, here, you want that one person in the